Now, I want to talk a little bit about an equivalent noise model, because I've talked now about how we can have thermal noise, how we calculate the total noise as KTB, and um, we want to talk now about an equivalent noise model. And the idea here is we've got some noisy receiver. And what I'd like to do is I'd like to treat the receiver as noise-free and then somehow compensate for the fact that it actually isn't with some simple model. And so the other reason is the receiver contains a lot of components, most of which are not resistors, but they still create noise. So we want to sort of find an abstract way to describe this noise. Regardless of what type of noise and at what stage it's generated, all the noise power is going to reach the output. And so as you can see here in the diagram, we've got some noise in, we've got some noise out. And if I ask you a quick quiz question, will the noise out be equal to or greater than the noise in? You should intuitively know it must be greater than the noise in. And so we want to figure out some way at a system level to represent the noise added by the receiver without having to get into what's inside of here. Okay? And so what we do is a concept called input referred noise. And so we have a certain noise in, and we're going to assume that we have a noise-free receiver. And in case you're wondering, this NF here stands for noise figure. And a noise figure of 1 means that we are noise-free. And we're going to talk about noise figure a lot more later in the modules. And what we do is we basically take the noise that would be generated in the receiver and we put it at the beginning, and we call it the equivalent added noise. And the way we do that is we basically figure out what would the noise on the output be, and that's because the Rx is non-ideal, so it adds noise. So the added noise, sorry. So we have the added noise. And then we figure out what the transfer function of our receiver is, and we take that added noise and we transfer it back to the input as an equivalent added noise. So let me just give you a quick example of that. Let's imagine our amplifier had a gain of 2. And I had noise that was, I'm just going to make up a number here. Let's say my noise was minus So the idea here is to simply add the noise to the input and make everything after it ideal. And it's also convenient because now I can compare the added noise to the noise in the signal in the input, and that really gives me a good idea. For instance, if the added noise was going to be much larger than my actual signal, I could tell right away that I was going to have a problem. So let's talk briefly about noise figure. Noise figure is the ratio of the signal to noise ratio in to the signal to noise ratio out. And so if we break that apart, as you can see here, so signal in, noise out, signal out, these two cancel, and we're left with noise out over noise in. And remember, noise out is equal to the noise in, right, plus the noise added. Right? And so that's what we get right here. And so these two just give us 1. And so the noise figure is 1 plus the noise added divided by the noise in. And you can see for an ideal receiver, the noise added would be 0, and a noise figure would simply be 1. And I just caution you here, once again, we can write ratios in terms of dB, and we can write them in terms of linear. You need to make sure you know what your units are when you're doing calculations. Particularly, notice over here we're adding, and so we need to make sure we're dealing with everything in a linear scale, not in dB. And so I've written over my notes here. So the noise added is simply the noise figure minus 1 times the noise in. And this is important, because in all of our equations in the future couple modules, you're going to see NF minus 1. And you have to remember, what is the 1 for? The 1 just removes the fact that the noise out is equal to the noise in plus the noise added. So the minus 1 gets rid of the noise in. And the total noise at the output is simply the noise figure times the noise in. And you can see right away why that's super convenient. Because if you give me a noise in and you tell me the noise figure of a component, you can tell what the total noise on the output is going to be. So with this model, SNR is not changed from here on out. That means that once we've referred all of our noise back to the input, we have an ideal receiver for the rest of the